Então, eu gostaria de convidar o Dr. Joris Vanlede para fazer a apresentação dele, Nautical, How to Keep Mud Under Control. Okay? Thank you.
Thank you and good morning. My name is Joris Vanlede. I'm affiliated to Flanders Hydraulics Research and would like to talk to you today about the concept of nautical bottom, how to keep mud under control, and I would like to apply it, the concept, to the harbor of Zeebrugge in Flanders. So Zeebrugge is a coastal harbor in Flanders. You can see the western Scheldt, and Zeebrugge is the protruding bit here. It gives out into the North Sea. The main activities of the harbor include liquid nitrified gas, LNG, and container terminals here. There's also an inner port here connected to a sluice, but I'll be mostly talking about this outer port. Now you can see it has an open connection to the sea. This is the North Sea. The color of the water, you can see there's a lot of mud in the water. There's a lot of suspended sediment. So there's also a lot of siltation in the harbor. There was already one figure mentioned by Han yesterday. This is an example of an LNG carrier doing a maneuver inside the harbor, and this is an example of the largest ship I think we have up to date in the harbor. It's about 400 meter length, 50 meters draft, and a bit more than 16,000 20-foot equivalent unit that we accepted in 2012 in the harbor. Now, it's a similar story as yesterday. The drafts of the ships keep on increasing, so there's a lot of pressure, or there's a question to keep this harbor navigable, to have it accessible for nautical purposes. So we talk about nautical accessibility. There are two operational limits that we have in Zeebrugge. The first is the cross component of the flow. I think we saw it a few presentations earlier. Also, this numerical result of cross component. We have used a similar methodology here in this harbor. And in our case, the cross component cannot exceed 2 knots, or about 1 meter a second for container vessels larger than 200 meters. And it cannot exceed 1.5 knots for incoming LNG carriers. It's a bit more strict for those. So this gives you an accessibility window. Ships cannot enter during the entire tidal cycle in the harbor of Zeebrugge. But more importantly for this talk is ships are also sailing above or sometimes in the mud. And that gives a second operational limit to accessibility that I will talk about. And that is related to the concept of nautical bottom. So first, this cross component of the flow. This is a numerical model result. The blue curve is the cross component of the velocity in this point just outside the harbor. And the ebb and flood flow in the North Sea, they pass through this point, and here these two bars are the two limits that I just talked about, 1.5 knots, 2 knots. So you can see that for some parts of a tidal cycle, the cross component of the flow is larger than this, which means that we have an accessibility window. The top graph is for the 2 knot criterion, the bottom graph for the 1.5 knot criterion. Anything that is colored means that a ship cannot enter. Meaning that, for instance, for incoming LNG carriers, the most strict criterion, only a limited part of the tidal cycle is available for a ship to safely enter the harbor. So that's already one limitation of the accessibility of this particular harbor. But as I said, I want to focus this talk on the second operational criterion, which is the nautical bottom. First I'll talk a bit about what we know about the siltation of the harbor. And I'll guide you through the evolution of how we define nautical bottom in this particular case. We ended up with a dual criterion, and that implied surveying and dredging practice. What do we know about siltation? About 4,000 to 12,000 tons of dry matter enter the harbor each tide, which gives you, it's about 5 million tons a year that annually get into the harbor and that has to be dredged out. That's quite a large cost for the government to maintain this harbor. It is a private harbor, but I work for the government of Flanders. The government guarantees the accessibility of this harbor to the Port Authority. So this is a cost that the government takes on itself. I'll use this definition of nautical bottom by Piank in '97 as a bit of a framework to frame the rest of my talk in. We'll go through it together. The nautical bottom is defined as the level where physical characteristics of the bottom reach a critical limit beyond which contact with a ship's keel causes either damage or unacceptable effects on controllability and maneuverability. Now, you might see, you notice that this definition, it stops at the level of physical characteristics. It leaves it up to, for every port, you have to translate this into a practical criteria. And this would imply then a practical measurement strategy. And I want to talk with you through how we defined this nautical bottom in Zeebrugge. It all started when I was 6 years old, so I wasn't involved, in 1986, with a measurement campaign in Zeebrugge on the physical characteristics of the mud. And this was a typical result then. What we see is, I'll go one back, on the left, so the vertical axis is depth. On the left we have a rheological measure, the rigidity of the mud, the resistance that the mud has to shear, the minimum shear that you have to apply to the mud for it to start to move. And on the right you have density over depth. Now first, these two lines indicate the typical acoustic reflectors that are used when we're measuring mud. The top one is a 210 kilohertz, the bottom one is a 33 kilohertz. As already mentioned in the talk of Professor Mehta yesterday, typically fluid mud is what is in between these two levels. Now first of all you see, and that's physically understandable, is that the 210 kilohertz signal, it reflects on the point where the density curve deflects. So here on top of this you talk saline water, and here the fluid mud starts. Here you get a volume fraction of solids in the water. Here the fluid mud starts, and this is where the 210 kilohertz signal will reflect. So this would be the top of the fluid mud, the 210 kilohertz. This 33 kilohertz, it reflects somewhere deeper in the mud, and we looked at it, and we looked at it again, and we didn't find a clear correlation between the level of where the 33 kilohertz reflects and a density. Now, this is the density story. Actually, we were more interested in 1986 on the rheological behavior, and what we found is that there's a rheological transition below the level of the top of the fluid mud, meaning that even below the top of the fluid mud, there's a bit more than a meter where this fluid rheologically still more or less reacts as water. It's black water. There is some sediment in it, but there's no rigidity. It has no structure yet. So there's this rheological transition. And then we translated that back to a certain density, and we went back up. So in short, the methodology they followed in 86 was you measure rheology over depth, you find a rheological transition, you link that to a corresponding density, and then you choose a critical density with some kind of a safety factor involved. And that's how we came in 1986 to the level of 1.15 tons per cubic meters for Zeebrugge. This was the criterion that we used from 1986 to 2004. Just for illustration, I'll show some other criteria that were developed around the same time. A lot of other harbors also chose this density criterion as definition of their nautical bottom. It is a practical criterion because you can easily measure density. It's more easy to measure density than to measure rheology in situ. But physically there's no direct link between density and rheology. So even in 86 we said, or older colleagues of mine said, that this rheology density criterion relation needs to be checked regularly. So we did. In 97, the same measurement campaign was done again. So again, we see a result of 97. We see rigidity, the rheological initial yield stress over depth. This is the 87 result again, with this rheological transition here. And in 97, we saw two rheological transitions. So something in these 10 years, the fluid mud package in the harbor had reacted to the dredging cycles that have gone over it over 10 years, because you dredge typically deep, somewhere on the 1.2 tons per cubic meter level, and when it silts back in again, you have a fluffy layer and it has to consolidate. And by doing it repeatedly, you might change the structure of the fluid mud layer, and that was exactly what happened in the harbor of Zeebrugge. So now we have two radiological transitions. So by that time, already the research hadn't stopped in '86. By that time, the research has been going on, and by that time, Flanders Hydraulics was already closely cooperating with the University of Ghent because also at that time this definition came into vogue, to focus on this aspect. So we wanted our definition of nautical bottom to be updated because we saw that the mud was changing, and we wanted to take into account the effect of mud on controllability and maneuverability. Now I won't go into detail into that because my colleague Evert, he will talk about this in the next talk. He will guide you through the flow that we followed then, so I can skip to the results. And from 2004 on, this is the new criterion that we were using. Suppose you have a ship of a certain draft that wants to enter the harbor. The new critical limit was defined as the 1.20 tons per cubic meter, a bit raised level, and a ship has to stay at least 10% of its draft above this level. Combined with that, it can penetrate in this 210 kilohertz, so in this top of the fluid mud, the ship can penetrate in it for a maximum of 7% of its draft. We found that that did not hinder the maneuverability of the ship. Again, Evert will talk you through the methodology that we followed. So but you see that from 2004 on, we end up with this dual criterion. We need to know both the level of the 1.2 ton per cubic meter and the level of the 210 kilohertz in order to define our nautical bottom and to steer our dredging works. So this is an example. Suppose you have a ship, you have the 210 kilohertz, the top of the soft mud layer at one level. You have the 1.2 tons a cubic meter, our definition of nautical bottom here. So you have to, a ship can be 7% of its draft in the top of the soft mud. It has to remain 10% of its draft above the nautical bottom. So you can see that it's always one of those two that becomes critical. If the fluid mud layer becomes too thick, then this criterion will be the most critical. If there's a thin fluid mud layer, then you have to guide this one. So as a government, we're steering the dredging works. We have to keep an eye on both levels. This means that we have to survey both levels, and the way we do that, the 210 kilohertz is pretty easy to measure for large swaths of the harbor. It's done acoustically. That's this line. And the density, we profile it in vertical profiles. We used to use a radioactive source, the Navitracker. Currently we're using the RayoTune used as a density tune, so it's more like an acoustic tuning fork principle. And these two data sets are combined to give an idea of the vertical structure of the fluid mud. And here you can see again that the blue lines, they're not exactly consecutive. These are two different vessels that did these measurements, so they don't match up exactly, but they tell the same story anyway. The dotted line is the 210 kilohertz. The blue lines here indicate the 210 kilohertz by the ship that did the density measurements. You can see that the 210 again reflects on the level where this would be pure water, where the mud density really starts to kick in. The black line indicates the 33 kilohertz, so it's even lower than the point where, up to the point where we can measure density, because these density measurements, they stop at a certain point because the equipment can't go that deep. And this brown line here, that indicates the level of the 1.2 ton per cubic meter, and this would be the level at which we want to keep it. So this is, well, this is a post-processing that we did of this data, but this is actually the way that dredging works are steered in Zeebrugge. So we keep an eye on both this level and the brown level here. Now this also has implications for the dredging practice in Zeebrugge. In 2012, in the summer, Flanders Hydraulics was called in by the government because they had a problem. The level of the 210 kilohertz, the level of the top of the fluid mud, it kept on being high. it didn't really react anymore to the dredging works. And as you know, because we have this dual criterion, if that is high, then that becomes the limiting factor. So for a short period of time, they tried, and that's the red box here, they tried to dredge on the level of the top of the fluid mud. Let me guide you through this graph first. On this axis we have time, and here we have tons of dry matter that are dredged per sailing trip. So each line is one dredging action. It's a it's a suction trailing hopper dredger going in and out the harbor. You can see that it's more or less continuously. Every day the ship comes in and out multiple times a day. It's 24/7. There's dredging in the harbor. Now in the red box, this was the time when they were aiming with their head of the hopper on the level of the top of the fluid mud. And then you can see that the efficiency of this dredging trip, it dropped significantly. The dredging vessel, it could only port a limited amount of solid matter out of the harbor, whereas in the green box, it aimed for the 1.2 ton per cubic meter, so the head was lower in the mud, and then it can get a lot more sediment out of the system in one go. So just to show that this dual criterion might have impacts on, or has an impact on our dredging practice that we have in the harbor of Zeebrugge. So I hope I've shown you that in the harbor of Zeebrugge we use a density criterion because we use it as a proxy for geological behavior. We needed a practical measurement strategy, and so we chose density. The update of the criterion was checked against ship controllability, and the nautical bottom definition in Zeebrugge has changed in time, has been updated, and is tailor-made. So I think it's always very dangerous this is a criterion, this 1.20 that we now use, is something that you cannot simply copy-paste from one harbor to the other. A nautical bottom definition implies surveying techniques and implies a dredging practice. More importantly, or more difficult, is the acceptance of such a criterion. If you would imagine that you're a captain or a pilot, normally this 210 kilohertz signal, it shows you where the bottom is, the hard bottom. And a ship can never touch a hard bottom because then there's damage. Unless it's in the harbor of Zeebrugge, 20 years of research has shown that a ship can have 7% of its keel, of its draft in this fluid mud. It still remains controllable. It's safe to do so. But to communicate that to the pilots, to the harbor authorities, to the captains of the ships, that takes a lot of time, and it's not easy because it's a pretty scientific message that you have to get across. So there's a huge importance in communication and in training of the river pilots for them to be comfortable with this way of thinking.